Okay, so now we learned the convergence concepts and the convergence orders, and let's study the two fundamental theorems in statistics. First is the weak law of large numbers, and the second is center limit theorem. So these two guys will be your friends in this course, and like anytime, whenever, what kind of econometrics course uh, you take, no matter what you take, they are necessary. So super important theorems, and I'm just telling you the result. Their proofs are quite not easy. It's been a while. I have seen the proofs, so I'm not so sure if I can prove them now. Anyhow, so the results are really simple. So first, assume IID obviously IID, and suppose that the expected value of the absolute value. Oh, by the way, it's my fault. I had to use norm of x, not absolute value. Norm of x is finite. So expectation of the norm of the x is finite. Then the sample mean converges in probability to the population mean, right? This is one, and central limit theorem is that for a random, like for any random vector, also IID, and the other assumption is that expectation of x prime x is finite, and then we have this convergence. So you multiply square root n. So it's starting from this here. This is the sample mean, and this is the population mean. So the difference between the sample mean and the population mean converges to 0 by the weak law of large number. And so it converges to 0, so you cannot study its distribution. It vanishes. So you have to rescale by like enlarging them by square root n. Square root of n is multiplied, then its distribution is stable and converges in distribution to a normal distribution with the variance equal to the variance of x. So it's a very interesting result, a powerful result, and you see how powerful the normal distribution is. And so, like as you can see, the only assumption for these two key theorem is this, which is really mild. So these two assumptions are like, so for example, it means that the random variable must have finite variance. So for this to be violated, you need a random variable whose variance is infinity. So there are some examples, but in most applications, it's hard to think about an infinite variance. So that means the central limit theorem and the weak law of large numbers are satisfied almost everywhere. So the assumptions are mild and the results are powerful. And so as a result, we can say this. Let's start from the sum. Sn, define a random sequence Sn as the summation of xn, random variables, from 1 to n. And then for the summation, we know that the mean of the summation is simply n times the individual mean times n times mu. And as you can see, it is finite, and n diverges to infinity. So it diverges as long as this is not 0. So if it is not 0, then always it diverges. So as a result, the random sequence Sn diverges, of course not converging to 0. So the summation diverges. It's not big O P1. And then to make it not diverge, you divide by n, then it becomes the sample mean, x bar. So summation divided by n is the sample mean, and then we know by the weak law of large number, by the weak lobe large number, the sample mean converges to a population mean, to the population mean. Therefore, you can say that the sample mean is a big OP1 because it does not diverge. However, you don't know whether it converges to 0 or not, because for this to be true, you have to have this equals to 0. But here, we don't know. I did not assume that the mean is 0 or not. So we cannot say this, but we may consider their difference. No matter what the population mean is, anyhow, the difference between the sample mean and the population mean converges to 0. So they have the difference is a small OP1. But it is small OP1, so obviously small OP1 implying it is a big OP1. But small OP1 means it goes away, it vanishes, it goes to 0. And we cannot study that. Therefore, we multiply square root n, and then after multiplying square root n, we have big OP1 because it converges to normal distribution, which is not a divergence. So square root n times the difference is big OP1, or you may write it as the difference is big OP 1 over square root n, right? So one of these, they are equivalent notation. And this is how we usually write the results of the weak lobe large number and center limit theorem. So you should be able to work with them flexibly. And okay, and so I believe it's easy. You just need to take the result, and the result is enough. And the next thing, which is also very confusing, is almost surely, or almost everywhere notion. So you may think almost is not so rigorous, but almost is a mathematical term. So if you learn real analysis or measure theory, then they define what almost means mathematically. So now think about this. Suppose that there is a function that depends on a random variable omega 1, or omega I, excuse me. So the function depends on omega I and a parameter theta. So and then what we are interested in, the continuity of the function with respect to theta or omega. So think about theta. So suppose that we want to say that g is continuous in theta at a certain point. But when to say that the continuity may depend on omega. I mean, so the function may be continuous for some realizations of omega, but may not be continuous for other realizations of omega. In that case, however, the thing so for example, let's think about this. So if you think about a function g, which is simply a kind of linear regression residual, so y and x are random variables, and theta is your coefficient parameter. And then in this case, the function is continuous in theta no matter what x is. Even if x is 0, still it is continuous because it's flat. So it does not depend on x and y. But think about this. G function is this. So g function is this, and suppose that we are curious if this function is continuous when theta equals to 0. And then the answer is, so as you know, this function is flat except for one point. It's flat, the function is flat, and then jumps and flat again. So there is only one discontinuous discontinuity point. So in this case, the function is continuous if xi is not the point. Everywhere except for xi. So 1 point is not 1 point. The only problem is from 1 point. Then still then, can we say then? But we need, suppose that in our analysis we would like to say it is continuous. Continuity will help a lot. Continuity will help a lot. Then still there is some way to say that. So suppose that 1 point has probability 0. Then it does not matter. Right, for example, think about continuous probability distribution. If x is a continuous random variable, then the probability that x equals to 1 point is always 0. Right? The probability of 1 point is always 0. That means the function is continuous everywhere except for probability 0. So that means everywhere. With probability of 1, the function is continuous. There is a point the function may not be continuous, but that happens with probability 0. So we don't need to worry about the 0 probability event. That is what we may use in our later analysis. Make sense, right? So that is, in this case, we say that G is continuous at theta 0 almost surely. Almost surely means there may be some points that this does not hold. So the continuity, or if you say something, something holds almost surely mean then something holds may not hold at some points, but those points have 0 probability. Again, something holds almost surely means that something may not hold at some points, but those points are probability 0. So probability 0, as you can see in this example. Okay, and the rigorous definition, it goes like this. So the probability that this holds is 1. So exactly that's what I. So similarly, for another example, if you think about max, it is so maximum function is flat and then kink, flat and kink. Then it is not differentiable at 1 point, and if you can ignore that probability, then it is differentiable. Similarly, like absolute value function is a V-shaped, and then there is 1 point that the function is not differentiable, which will not be a problem if that point is probability 0. So, and as you can see from those explanation, in many cases, almost sure is enough because probability 0 does not matter. But one important exception is the Taylor theorem. Later, I will tell you again at that time. So almost surely is an important concept that that's not that difficult, but you may not be familiar with. Okay, we'll continue to another theorem. So there are a bunch of theorems coming later. So see you in the next video.